Okay, so let's look at the data that we had on the on the second video on the analysis of glucose and the analysis of glucose in Verbrandt's wax. So, diba? This is the data that we had. So, this is the data that we had, diba? So, if you look at the data class, so if you look at the data, we have 20.5, 20.55. So, let's just look at the batch 1. 20.52, 20.5, and 23.51. Now, if you notice, 23.51 is like an outcast, diba? Because it's very far. I mean, it's quite, not very, but it's a little bit far from the other measurements. So, you have to check you have to check whether to retain or to reject that data. So, in order to do that, we use the Q-test. So, the Q-test, okay, so the Q-test is a test to, this is basically a test whether to reject or to retain one of your measurements. Okay, so this is the formula of the Q-test. So basically, Q is equal to Q bad, or this is the X bad, which is the questionable measurement. So in our case, this is 23.51, and then we have minus X next, which is the measurement closest to the questionable value. So, ang pinakadool sa 23.51, which is 20.55, diba? 20.55. Divide that with the range. So, this is, the denominator is just actually the range. So, lowest value ang X low, ug ang highest value ang X high. So, that's X high minus X low, which is 20.50. And this is equal to 0.983. This is equal to 0.983. Now, in the Q test, you actually have a Q table at different confidence interval. Now, in this case, this is at 90% confidence interval. So, these values class are located at the appendix, or you can just search this. Okay, so these values changes depending on the confidence interval. So at 90% confidence interval, the Q for measurement for n number of measurements. So for n equals 5, so n is the number of measurements, is 0.64. Now, if Q calculated is greater than the Q in the table, then you have to reject. Now, in this case, we have to reject. So, therefore, if Q calculated is less than that of the Q table, then we have to retain the value. So in this case, at 90% confidence interval, Q calculated, or which is 0.983, is greater than the Q table, which is 0.64. That means we have to reject 23.51. Okay? And since we need to reject that, that means if we calculate the mean, we only need to calculate the mean for these 5 measurements and the standard deviation. Okay? Okay. Now, in an analysis class, oftentimes, the instrument will just give you an absorbance. I mean, a different readout. So it's not a readout that will give you the concentration directly. Okay, so it has another kanang readout. So you have to convert that into a concentration. And in order to do that, oftentimes you need to make a calibration curve. So this is when we do regression analysis. So this is how you make a calibration curve. It's actually simple if you just try to understand it. Okay? So ang basic concept of a calibration curve is that the basic concept, okay? This is the basic concept. You just make a curve, okay? An XY curve. So this is the concentration, and this one here is the readout, or for example in UV-Vis, which is the most common, we have the absorbance. So mo na ang readout sa instrument. Readout meaning this is what you get, the data that you get from the instrument. So the data that you don't get concentration from the instrument, you get absorbance, okay, in UV-Vis, in the case of UV-Vis. So you need to get some line which has to be more, well, which has to pass the standard of, which is an R squared of almost 1, okay? Actually, in analytical chem, it has to be at least 0.9998. It has to, or up to 1. Up to 1, okay? 1.0000. That's the best, because this measures the best fit. So you need to make several points. So at that concentration, the absorbance is this. At this concentration, the absorbance is that. Okay? So that's basically what you need in order to get the concentration of your sample, of your unknown. Okay, so this is the case. You have this unknown sample in a volumetric flask. Okay, forgive me for my drawing. So you have this unknown sample in a volumetric flask. So all of this was done accurately analytically. Okay, so measured 50.00 exact volumes. Okay, so all of these were done analytically. So let's just assume you already have the sample, and then you read this in UV-Vis. Now UV-Vis will give you an absorbance value, not a concentration value. So for example, the absorbance value for this one is 0.380. Okay, so oops, sorry. Okay, so let's say you have that absorbance value. So what should you do? So for example, your analyte here, your analyte is copper. Okay, oops, sorry. Okay, so for example, your analyte is copper. Okay, so you need to know how much copper is there in your sample, and the UV-Vis only gave you an absorbance of 0.380. You don't know the concentration of copper, therefore, and you are looking for the concentration of copper. So in a calibration curve, what you need to do is to prepare samples. I mean, to prepare standards. This is what you call standards of known concentration of your analyte. So you get a copper nga substance like copper sulfate, for example. You dissolve it, make copper sulfate solution, and then you prepare 0 ppm or 0 molar, it depends on you. So 0 ppm copper, 5 ppm copper, 10 ppm copper, 15 ppm copper, 20 ppm copper. Okay, it doesn't matter how many points you need, you'll make, but the more points the better. Okay, what if mo deviate siya, diba? What if after Q test, you need to remove two values, so it won't be as accurate anymore. So the more the better. So in many cases, class, we just use five points. So when I say 5 points, it's 5 points sa kiniba in this graph. Okay, so this is the concentration of copper. So this concentration is known. Okay, so you just prepare this in the same manner as you prepared your sample. So you put that in a volumetric flask still, and then you analyze that with UV vis, and then UV vis will still give you an absorbance. So the absorbance, okay, so for example, this gave an absorbance, so maybe noise ang 0.1, diba? Then sorry, noise is 0.001, and then it gives you an absorbance 0.118, 0.2 220, 0.3340, 0.442, okay, something like that. Okay, so for example, this is the data that you get. So this one, you prepared these. Ang 0, it means distilled dry. This is just distilled water, so it's like a blank. Kay when you prepared these other 4 samples, you use distilled water. Okay, so of course that's your blank. So this column is the absorbance. So this was reported by the instrument. Okay, so this is what you got from your analysis. And then what you need to know is the concentration. You don't need to know you already know the concentration of these, right? So you just plot that. Okay, so let's use XY graph, an XY scatter. Okay, so let's use an XY scatter graph. Okay, so this is the XY scatter. So as you can see, oops, okay, so as you can see, this XY scatter shows concentration. Okay, so as you can see, diba, 0, 5, 10, 15, 20. So the x-axis is the concentration, whereas the y-axis is the absorbance. Okay, so what you need to do is you get a best fit line. So add trend line, and you just say, you just click, I'm sorry, that's linear. Yeah, that's linear trend line, and you display the equation on chart, and you also display R squared on chart. Okay, so once you have that, so your data, even it's not 0.998, but it's okay. So because this is an environmental sampling. Okay, so actually it should have been 0.9999 or 1.000, but it's okay. So for discussion's sake, let's proceed with this one. So we have the equation of this one is y equals 0.0221x plus 0.0034, which is just the slope of a line. So that's y equals mx plus b. Now take note that the absorbance of your sample is 0.380. It must be somewhere between 15 to 20, right? Because 0.380 man yung absorbance. The higher the concentration, mas dako yun ang absorbance, right? So your 0.380 must be somewhere here. And how would you get that? You just substitute 0.380, that's y, diba? Kay absorbance is the y-axis. So you substitute y with 0.380. and then you find the x, and you get the concentration of your sample. Okay, so let's try. 0.380 equals 0.380 equals 0.0221. You have to befriend your calculator. Your calculator could also give this to you, could give you an equation of a line. Okay, so try to befriend your calculator. Plus 0.0034 and find x. And the answer is 0.43, if I'm not mistaken. So 0.430 is a concentration. Sorry. 17.04 ppm is the concentration of your sample. Okay, now this is what you call as an external calibration method. Okay, so this is an external calibration method. Okay, there are other methods actually, internal standard addition method. So basically, ang internal standard is you add, so you mix. Ang internal standard is ang internal standard is just the same kini external calibration, except that before nimo gi-fill to the brim sa volumetric flask, you add constant amount of sample. So na kay sample volume nga add, like for example you add 10 ml. Okay, in ml. Okay, the purpose of internal standard is internal standard nga method class is, I mean standard addition rather, sorry, it's standard addition. Ang purpose of standard addition class, so this one is kini, it's just external calibration. If you add constant amount of sample, like 10 ml sa kada standard nimo, that's called standard addition method. So the purpose of this is, ang advantage ani niya is that your solution, so ang kini nimo nga solution, imong standards will have almost the same matrix as your sample. Kay whatever constituents is in your sample will also be present in your standard, diba? Because you added 10 ml of the sample. Okay, and the last one is internal standard, which we won't discuss because that might be too complicated. But ang basic, ang gist ra gid niya is that you use two standards para i-ratio nimo ang duha ka standards para makancel ang error ba. Kay if i-ratio nimo, makancel ang error sa numerator, makancel ang error sa denominator. Okay, but we won't go into that. So the most common ra nga ginagamit is external calibration and standard addition method.